Hello, Earth and Space Science. In this video for climate change, I hope to accomplish two things. First, to give you my kind of overview of just where we're going with this entire topic and a lot of things you know, before I focus in depth on the first topic, which is radiative forcing and what your assignment questions are about. It would be helpful if you if you have paper or something to write with, kind of follow along as I build the overall flow chart today. Being able to see that in front of you on one page, knowing where we are, where we're going, will help a lot over the next couple of weeks to have that kind of as a resource for you. Even though I'm not grading it along with the questions, it's really helpful to do. I hope to break down climate change as simple as I can into its really key components that I feel the most important. I think a lot of people make this topic too complicated and then just confuse people. I'm just going to try to keep it as simple as possible with what you really need to know and the key points. So let me plug in my document camera here so I can make this. There we go. Awesome. So let's start here. I'll even out my paper. The first key is that we'll talk about a topic called radiative forcing. As kind of our key idea that starts off this whole discussion of what we call as climate change. I'll put that heading at the top. Climate change. There you go. And as we look at the table today that talks about radiative forcing, you're going to realize that the key idea is really a strong understanding of greenhouse gases. Because greenhouse gases operate in what we call the greenhouse effect. Let's do a simple picture for you here below of what we call the greenhouse effect. So here we have planet Earth, and of course, in the sky above us, we have the sun. That sun provides us with visible light that hits the surface of the Earth. So this is visible light. And when that happens, the Earth heats up. You probably experience this well in the summer. You're barefoot, you walk on, let's say, pavement or sand, and it feels hot. Why does it feel hot? Well, it's been heated up by the visible light from the sun. And when something heats up, it emits a different type of radiation. And that's called infrared radiation, or IR radiation. Any actually body that's warmer than its surroundings emits infrared radiation. You right now, because you're warmer than your surroundings, are emitting infrared radiation, or what we know as heat, basically. Some of that heat, or some of that infrared radiation, escapes out into space. That's completely normal. But there's also what we call the greenhouse effect. So some of this infrared radiation, instead of just escaping into space, is going to hit what we call our greenhouse gases that are in our atmosphere. They're going to hit carbon dioxide, methane, mainly the ones we're talking about. And when this happens, when the infrared radiation, instead of escaping into space, hits these greenhouse gases that are accumulating in our atmosphere, it re-radiates the infrared radiation, or traps that heat in our atmosphere instead of it being allowed to escape. This greenhouse effect is actually not always a bad thing. For the most part, it's a good thing. If there was no greenhouse effect at all on Earth, the average temperature on Earth would be 32 degrees Fahrenheit, or just about freezing, and almost all of the Earth would be covered with ice. So a certain greenhouse effect is good. What we have today, of course, is a one that is too enhanced. It is too much, and we're going to see that later in our graphic. But this radiative forcing, the greenhouse gases, the greenhouse effect, lead to increased global temperatures. And we're going to get into how much they've increased, but I will pull out a key phrase right now called the last 5 hottest 5. And this is since we started taking good temperature records, which is 1881. Since 1881, so what are we, almost 140 years now. The warmest 5 years in that last 140 years have been the last 5 years, which is pretty startling. And you'll see that in a graphical form later. These increased temperatures are leading to changes to the atmosphere that we'll look at, the biosphere, the living things, the cryosphere, the ice, and finally the hydrosphere, the water. Everything on Earth, the atmosphere, the biosphere, the cryosphere, the hydrosphere, are all changing because of this temperature change. Some of those changes actually, we're going to learn, are fine. Some are quite worrisome though. But there's another thing going on here that's important that we're going to talk about. There's what's called feedback. There's 2 types of feedback. There's what we call reinforcing feedback. This reinforcing feedback is going to increase warming. It's going to be warming that leads to a change that leads to more warming. But there's also what we call balancing feedback too. Some changes are actually going to cause lower temperatures, so decrease in warming. And we'll look at both of those, which is stronger. What are we seeing today? So there's our basic overview. I would kind of recreate that if I was you. So you have that to work from as we go through each of these topics. Today, we'll be focusing on this one, radiative forcing, and it's what you'll have your questions about. All right, so let me share my screen with you so I can show you the key graphic that you're going to use to understand radiative forcing. And here we go. This is from an important climate report published in 2000, a little bit after 2005. So that's why it's using 2005 as its max year. What this looks at is what's called the Earth's energy balance. So we look at pre-industrial times, so 1750, so we're talking about pre-Revolutionary War times compared to today, and how the Earth's energy balance has changed. Anything over here on the right has caused the Earth to store more energy in its atmosphere and is warming us up. Anything on the left here in blue are things that are actually cooling us down, causing the Earth to store less energy. These are all related to human activities, this top of this table. Here is natural processes that are disrupting the Earth's energy balance. And here's the total net effect of all of these human effects from above. The first thing I want to point out to you is, just like I had you focus on before, is the greenhouse gases. Notice that these greenhouse gases have large bars: carbon dioxide, methane, N2O, and the halocarbons. These are all greenhouse gases. They all do the exact same thing. They trap that infrared radiation that's being released from the Earth as the sun warms us, causing the Earth to store more energy. Particularly look at this CO2 bar. Gigantic compared to anything else that's disrupting the Earth's energy balance since 1750. We also have ozone, O3, in the troposphere where we live that's warming us up. Stratospheric, so that's the layer above the troposphere where like planes fly, that's warming us up. And then black carbon on snow. That's causing a change in what we call the surface albedo. Basically, black carbon makes the surface of the Earth darker. When it's darker, it absorbs more sunlight and we warm up. But there are also things that are cooling us down too. Ozone in the stratosphere. Other land use changes are actually making our surface lighter and more reflective that are cooling us down. And then what we call aerosols. So these are like sulfur dioxide particles that are emitted from power plants and such that are causing either, they either directly block the sunlight, causing it never to reach the surface, or they create clouds that block the sunlight so it never reaches the surface and never warms us up. But if we take all these into account, notice that we are disrupting the Earth's energy balance and making the Earth store more energy than it did in 1750. This is the error bar of how confident we know that it's probably somewhere between here and here, but this is kind of your average of the disruption in the Earth's energy balance. But you can also see that there's a natural process too going on, and that's the sun. Since 1750, the sun has continued its natural progression of slowly getting warmer and warmer and warmer, emitting more and more energy that's arriving at the Earth and causing us to have a slight increase in the Earth's energy balance. And we've talked about this already this year. We said that this trend over the next billion years will eventually create the Earth into a Venus-like place rather than an Earth-like place like we know today. But look how little of an effect that is compared to the human effect. And most of that human effect is all, directed at this carbon dioxide problem that we have. Let's look at one other thing before we go, and that's this. So carbon dioxide, it is emitted when we burn fossil fuels. We burn coal, we burn oil, we burn natural gas, we burn gasoline. Anything like that emits carbon dioxide basically from the smokestack or from the tailpipe or whatever. This is taken from Hawaii and shows carbon dioxide levels in the atmosphere since 1950s up until today. Notice that this is an average, this black line, but in the 1950s, we had below 320 parts per million CO2 in the atmosphere. Today, we're well above 400. So there's been a drastic change in this most important radiative forcing that is causing the Earth to store energy. So when you look at your questions, you can refer back to this video. You can look at different ideas that I've talked about here, different things that are warming us up, cooling us down. What is the cause of climate change today? Those things, and good luck.